In a previous video on this channel, I explained the model of tau-equivalence and showed how this model of tau-equivalence can be fit in the Mplus software. In this video, I want to show you another model of classical test theory that's called the model of essential tau-equivalence. And so before we get there, I want to show you an application of the model of tau-equivalence to a different set of variables than the ones that I showed in the previous video on the tau-equivalence model. So here I'm fitting this model of tau equivalence again to two variables y2 and y3, and you can see here that in this input file the loadings are fixed to 1, which is implied by tau equivalence. The intercepts are both fixed to 0, which is also implied by tau equivalence, and the only parameters that we're estimating are the tau or true score factor mean, the true score factor variance, and the two error variances. Now let's take a look and see what happens when I fit this model of tau equivalence to those two variables. And you might have guessed it, in this example here, contrary to the previous example, this model does not fit. For the previous variables that I showed in a previous video, the model fit very well, but for those two variables here, it does not fit. The chi-square is statistically significant, and so therefore this model is rejected. Now, why would that be the case, and what can we do about it? So why does it happen that a model of tau equivalence doesn't fit? In this case, it's pretty clear because we have just two variables, and so the only reason why the model of tau equivalence here could fail is if the two variables had different means. And so you can see that in this example, the mean of the test score variable y2 is somewhat lower than the mean of the test score variable y3 by about 1 point. So that shows us that the test y3 is a little bit easier than the test corresponding to y2, because on average individuals here scored higher on test 3 than on test 2, and so that indicates differences in difficulty between those two tests, and that's not in line with the assumption of tau equivalence. So tau equivalence requires tests that are equally difficult, that have the same means. That's implied by this assumption of tau equivalence. So that's in this case the only reason why we could see any misfit. The only other reason why this model wouldn't work is if the tests were not at all correlated. So that also would be against this assumption that they measure a common true score if they didn't correlate. But you can see the correlation here is quite substantial. So that is actually in line with what we would expect, that there's a strong positive correlation between those tests. And so the reason here why this model doesn't fit is because of the differences in means. So there must be a significant mean difference. Now, how can we account for that in cases where, let's say, we don't want to or we cannot change the tests that we have as indicators, and so we can't make them tau equivalent, but we still want to use those tests, for example, or we want to find out about the reliability of these tests, or we want to use these tests in a measurement model in research, or in a measurement model to do other things with those measures. Then what can we do if we find that tau equivalence doesn't work? And that brings us to the model of essential tau equivalence. With essential tau equivalence, we're making less restrictive assumptions than with tau equivalence. So it's a strict tau equivalence implies that the variables must share the exact same true score, and that implies that they must have the same means. Now, with essential tau equivalence, we're relaxing that assumption a little bit, and we're no longer saying that different variables have to have the exact same true score, but rather that they have to measure essentially the same true score, but that they can differ by an additive constant. So we add a parameter to our measurement equation, which here is indicated as alpha I. Alpha I is a test-specific constant, or additive constant, we could say. And we also say it's an intercept. And so this intercept constant accounts for mean differences between the tests. So they can still measure the same construct. So those could still both be, for example, measures of intelligence. However, one intelligence test in this case is more difficult than the other one, as reflected by those different means. And so this intercept parameter can be used to take that into account. This intercept parameter exactly will capture the mean difference. Now, what does the model look like then with this intercept parameter? So we still have two measures here. We have a common true score. Loadings are still fixed to 1 for both of these indicators. We still have our error variables here. We're still estimating the true score variance and the true score mean. We're also estimating the error variances, and in addition we're estimating one intercept parameter. We don't have to estimate both intercepts, and in fact this would actually not be possible. It would lead to an under-identified model if we were trying to estimate both an intercept for the first test and an intercept for the second test. Rather, we're using test 1 as our reference test, and so for test 1 or y1 we do not include an intercept, and so then what happens is that test 1 becomes the test that identifies, so to say, the true score variable tau, or we could say the true score variable tau then is equal to the true score variable for that test y1, whereas y2 is only essentially equal to this, or has a true score variable that's only essentially equivalent to that true score variable for test 1, because it can differ by this constant value alpha 2. So this additive constant indicates the mean difference by which y2 can differ from y1. We can still use this model to determine reliability in the same way as with the strict tau equivalence model. The additive constant does not change the equation for reliability, because reliability is purely based on variance components, and the additive constant is irrelevant for those variances. So this is an alternative model that you can try when tau equivalence does not fit, because the tests have different difficulties, because they have different means. Then you can try a model of essential tau equivalence. You can use one test as reference, and you estimate the additive constants or intercepts for all other tests, and then these intercepts give you the mean difference of these tests relative to the reference, as we will see in Mplus. So let's take a look at how this essential tau equivalence model is fit in Mplus. So let's go back to the input file and now specify the essential tau equivalence model. How do we do that? We do that by only slightly changing this subcommand here, or the statement for the intercept. So now we only set the first intercept to 0. That's our reference indicator that identifies the mean and variance of the true score factor. And then the second intercept is now freely estimated, so we delete the @0 here, and instead we can put a star, if we like, to indicate that this intercept is now being estimated. So we add this additional parameter to the model, and then we have a model of essential tau equivalence. Now let's take a look at what we get for this model and how we interpret those intercepts, or this one intercept that we're now estimating. First of all, when you fit this model to just two measures or two tests, then it will always be saturated, because in this model we now estimate 5 parameters: the true score variance, the true score mean, the 2 error variances, and the intercept alpha 2 for the second test. And we have 5 pieces of information with 2 variables: the 2 means, the 2 variances of the observed variables, and their covariance. And so this model is saturated. It must fit perfectly. The only way to basically to reject this model would be if the tests weren't correlated. Then it wouldn't work at all. Then you can't get a true score variance if you don't have a covariance between the measures, because the covariance between the measures is what identifies the true score variance. And so then that would be the only way to reject it. Other than that, as long as the tests are positively correlated, as long as they have a positive covariance, then this model will always fit with just 2 measures. If you have 3 or more measures, the model will be over-identified, because then the model has a constraint for the covariance structure. It implies equal covariances of all measures, and so then you would have positive degrees of freedom, and the model would be testable. But with just 2 measures, a model of essential tau equivalence is not testable. Nonetheless, we get parameter estimates, and they're valid. We can interpret them. They're trustworthy, so to say, because we're perfectly reproducing the observed data structure. You can see that now we have an additional parameter here. In addition to what we had in the model of tau equivalence, we now have the intercept for the second variable, and you can see that intercept is statistically significant, and it's positive. Now this positive intercept reflects the fact that the mean for the second test, or for test 3, was larger than the mean for test 2. We can see that by taking a look at the means again. You can see that the mean for Y2 was 33.099, the mean for test 3 was 33.888, and that difference, 33.888 minus 33.099, is exactly what this intercept is. So that gives you the mean difference, and also you can see that the mean of the true score variable is exactly equal to the mean of Y2, because Y2 is the reference variable, and so that variable identifies the true score mean, or the mean of that variable, I should say. And so then the intercept can be added, so to say, to that mean, and then you have the mean of the second, or of Y3. And so therefore this intercept can be interpreted as a mean difference parameter, and the test of significance tells you whether there's a significant mean difference between Y3 and Y2, which here is the case. So you could think of this as a fancy paired samples t-test that looks at those means for the same people across those two variables and compares them for differences and looks at whether there's a significant mean difference. And so that shows you why the model of tau equivalence didn't fit, because this mean difference is statistically significant, and that was what led to the significant chi-square test with the model of tau equivalence, where we implied equal means. Now we're no longer requiring equal means, and we can see that that's better because that mean difference is significant. You can still look at reliability by looking at R squared, and so those reliability estimates can be interpreted as before. It shows us that 62.8% of the variance in the first measure is true score variance, and 67% of the variance in the second measure is true score variance. So those measures are not super reliable. There's a lot of measurement error variance here in these measures. So hope you found this useful to learn more about the model of essential tau equivalence and to learn more about what you can do when the tau equivalence model doesn't fit. If you're more interested in psychometrics, classical test theory, check out the description for more workshops and videos. Please subscribe to this channel and leave a comment in the comment section, and I'll see you next time.